Hello, my name is Jeff Shallenberger. I'm going to talk about some of the unique capabilities we have at the Materials Characterization Lab for measuring electronic properties on materials. Some of the properties that we're going to talk about are mentioned here on this slide. A lot of these are obtainable through a very unique surface science cluster tool that we have in Materials Characterization Lab. It has 5 different spectroscopies all in one, and it resides in the basement of the Millennium Science Complex. We have a couple other techniques that we'll also mention in this presentation for getting some other information, including band gaps and carrier concentrations. So just a quick overview on energy bands of different types of solids. As a review and introduce a couple of the concepts here, we have metals, semiconductors, and insulators, with one of the big differences between them being the size and existence of a band gap on these materials. So all the parameters we can measure here using multiple of the techniques that we have that we'll talk about in the coming slides, including the vacuum level, the work function, the band gap, and a few other parameters, including the valence band maximum, conduction band minimum. So one of the principal techniques that is part of that surface science cluster tool is a technique called X-ray photoelectron spectroscopy, which allows us to access both core and valence electrons of solid materials. And if we look at a simple metal, in this case gold, and we look at the valence electrons, so we're looking at the very weakly bound electrons in the material. They're quite weak in XPS spectrum, but we can see that on a metal like gold that we have electrons right at 0 binding energy. So this is the Fermi edge, or the Fermi level of this metal, as all metals should have, and that should reside right at 0. So not too interesting. All metals should have that, but just a quick example of it. If we look at a semiconductor, in this case, a P-type silicon or an N-type silicon, they have the same nominal band gap, but they have different valence band maximum as a result of the different types of doping levels in these two materials. So we would see a difference in the valence band maximum between a P and an N-type. And lo and behold, if we take two pieces of silicon and collect this valence band region, we can see difference in the onset of these. So they don't have a signal that comes right down to 0 electron volts like the metal they did, because they have a band gap, but they are shifted relative to each other for both the P and the N type. So to measure the band gap, first of all, the definition of it is it's the difference between the top of the valence band and the bottom of the conduction band on a material. The techniques that we have available to us in MCL are REALS, reflection electron energy loss spectroscopy, and UV-Vis, ultraviolet visible spectrometry, or we can combine 2 different techniques, ultraviolet photoelectron spectroscopy and low energy inverse photoionization spectroscopy, which we'll talk about later to get band gaps for particular materials that have quite low band gaps. So let's turn our attention to REALS, or reflected electron energy loss spectroscopy. It's a relatively simple technique. We bombard a very coherent low energy beam of electrons onto a solid sample. In the instrument we have with an MCL, we're typically looking at anywhere from 1 to 2 kilovolt electrons. Those electrons bounce off the sample surface effectively and are detected back at our spectrometer. And importantly, the atoms in the near surface where these electrons interact with it can lose energy in very discrete amounts. And that results in information that we can leverage to determine the band gap. So if we look at a wide band gap material like aluminum oxide here on the left, first of all, the spectra are shown here with shifted to energy loss. So in this case, we've used a 1 kilovolt beam to generate this. And we see a very, very large amount of electrons come back with nominally the exact same energy that they went in with. This is called our 0 loss, or our elastic peak. So this would have been our 1,000 volt electrons that came in and came out at 1,000 volts. And we've shifted these now to measure energy loss to 0. The area that we're interested in for band gap determination is this weak little signal right in between our 0 loss peak and the onset of our elastically scattered electrons. And what we see is that there is a gap. There is a region where there is no signal, and this is the definition of the band gap. And so to measure the band gap, it's a relatively simple measurement. We look at the distance between our 0 energy and our onset. And we basically do two linear fits, and we look at the point at which these two linear lines intersect, and that is a direct measure of the band gap on a material like this. So we can see aluminum oxide on the left, a very wide band gap material like SiO2 on the right, which has a band gap of greater than 9 electron volts on the left. And we can extend this measurement all the way down to, in our instrument, about 2.5 to maybe 2.7 EV band gap materials. There's an alternative way of measuring the optical band gap in MCL using a technique called UV-Vis. And in this case, we can extend the measurement lower in band gaps down to half an electron volt material and up to 5 EV by doing a very different type of measurement and looking at the optical band gap that we measure on a material. So another parameter that's important to people that are making devices and electronic materials is the work function. Work function is the difference between the Fermi edge and the vacuum level, or another way to put it is the energy required to remove an electron from the sample surface. So for this, we have 3 different techniques: XPS, UPS, which stands for ultraviolet photoemission spectroscopy, and Kelvin probe force microscopy, which is a very different atomic force microscopy based technique, which is useful for measuring the relative work functions. A little more challenging to measure absolute work functions on that. So to measure the work function via UPS, we look at the onset energy. So first of all, we apply a bias, in this case a 5-volt bias to the sample surface, which essentially separates the weak or the low energy secondary electrons from the onset electrons here that we're interested in here in the measure the work function. And we really are essentially looking for this steep increase in signal that we get from this secondary electron cutoff value that we see here. And from that, by subtracting that value from the bias from the energy that we measure those electrons at, we can directly measure the work function of a material. So in this case, we're looking at, I believe, a piece of gold or silver on this sample surface, measuring the work function. A third parameter that is important to folks making devices is the valence band maximum. This is the highest energy level in the valence band. It's also, for organic materials, called the HOMO, or highest occupied molecular orbital. And this is the onset position where we see signals start to appear in a material similar, analogous to what I showed in the P and N-type silicon a few slides ago here. So in XPS, again, we have access to core and valence electrons. In this case, we're going to be looking at these weakly bound electrons, which don't have a whole lot of intensity in an XPS measurement. And we're looking at the distance between the Fermi edge and the first onset of electrons from the valence band maximum. And what's shown on the right here is a material that has a valence band maximum of 3 electron volts. So this can be measured with XPS or with UPS. They're very comparable measurements. The main difference between them is the energy of the excitation source. The problem with doing it with XPS is that the signal strengths are relatively weak. This is the valence band maximum or the Fermi edge of a piece of silver acquired on our XPS instrument here at MCL, and you can see that we only have about 100 counts per second in this signal. And if we were to look at why or what the advantage is for using ultraviolet photons versus X-rays, we can see it from this plot here from a very old paper. And it's related to the probability of these electrons being generated, which is something called the photoionization cross-section, which is plotted on the left axis here. So if we look at the energy of our X-ray, the aluminum X-ray that we use in XPS, it has about 1,487 electron volts of kinetic energy. And for a given valence electron, like an oxygen 2p here, we can see a given cross-section, 2 times 10 to the minus 4. If we look at that same electron using ultraviolet light with a kinetic energy of 21 electron volts, we can see that we have about a 50,000-fold enhancement in the photoionization cross-section, meaning for every photon going in, we have 50,000 times more likely to generate that, to liberate that photoelectron from the sample. So this is really the main advantage of using UPS in these types of measurements. So if I look at that same material that I looked at for silver, where we were only getting about 100 counts per second, here we're now getting 25,000 counts per second. There's also another advantage to it in that the energy resolution of that light source is much better than it is on our monochromatic aluminum source. So the energy width, the resolution of this is only about 140 millielectron volts versus 340 millielectron volts when we do XPS. So we see this huge enhancement of signal and this enhancement in energy resolution when we do ultraviolet. Now, our instrument, I should point out, has both. And if we want to measure the valence band, we frequently measure it with both because there are certain advantages and certain materials that are better off with one or the other. So it's usually preferable to do both measurements on the same sample. So UPS, ultraviolet photoelectron spectroscopy, can really only access the valence electrons. We're leveraging in both techniques the photoelectric effect. So the kinetic energy of the electrons we get off, by definition, has to be less than or equal to the kinetic energy of the photon that we're using to generate them. So in this case, we only have 21 electron volts of kinetic energy, which means the most we can get is a 21 electron volt photoelectron off of the sample, and that largely limits us to the valence electrons or some very weakly bound core electrons. So here's a spectrum for scandium nitride film, where we're looking at the valence band maximum here. It's about 4 electron volts in this case that we're showing on this inset here, where we're looking at the linear intercept between the background and the onset of signal strength here on this material. And that's how we're typically making these measurements. Now, I should preface this that a lot of these measurements, certainly the valence band maximum and the work function, require that the sample be grounded. It be semiconducting or conducting. This technique for measuring these particular parameters does not work very well if the sample is insulating. So we go to great lengths to try and ground the sample to the spectrometer. The band gap measurements through reels are a different story. That measurement is not really dependent on the sample being conductive, somewhat surprisingly. All right, so the band gap, normally is this region where there are forbidden electrons. So there cannot be any signal in there, but that's not, from a practical point of view, that's not always how things work out. There are generally no losses in the band gap region, but gap states do occur and can dramatically affect properties. And these techniques can be used to measure those gap states in materials. So an example I'm going to show here is from a material where we know the band gap from reels is about 3.4 electron volts. And we're now superimposing some XPS valence band spectra here. And we can see the valence band maxima is going to be the intercept between this vertical line or this steeply sloping line in our background here. And it's going to be around 2.5 electron volts. But if we blow up this little region in blue here, we can see that there is some intensity that sits within the band gap. So these are gap states in this particular material that we can see by XPS. If we do this by ultraviolet photoelectron spectroscopy, we're looking at the same region of the spectrum, and we have the enhancement and signal strength that is inherent to UPS relative to XPS. So we see much larger, much less noise in our signal, and we see this same kind of gap states here. We can take it a step further and do reels, reflect that we showed earlier. And here we can now see this weak shoulder that all sits at the same relative position to the Fermi edge, about 1.3 electron volts. So we've got 3 independent techniques that all measure the presence and energy of the gap states in this particular material. Now, there's some other information that's available from reels, and that is something that we're just starting to work on now with some of our researchers here at Penn State. That is studying certain plasmonic properties. So in the electron energy loss spectroscopy, we frequently see plasmon losses. And there is a specific area that's of interest to people studying plasmonic materials called the crossover energy, which is an area or an energy that this system undergoes a change from a metallic-like to a dielectric-like optical response. And it manifests itself as a small little peak sitting next to our zero loss peak. So this is some reals data on a hafnium tantalum carbide material here, with the inset showing this small loss feature here at about 2.1 electron volts on this material. Another important parameter to people designing devices is the conduction band minimum. So this is the other side of the band gap. So what we were talking about so far was the total band gap and the valence band maximum. So you can calculate or estimate the conduction band minimum if you know those two parameters independently. And that's typically or frequently how we do it here at MCL. But we're limited. Our real system can only measure materials with band gaps greater than about 2.5 electron volts. So if you've got materials that have narrower band gaps and you're interested in this information, we need an independent way of either measuring the conduction band minimum or the band gap or both. UV-Vis gives us an independent way of measuring the band gaps down to about 1/2 an EV. And then we have a relatively new technique here at MCL called LIPS, for low energy inverse photoemission spectrometry. And in LIPS, as the name would imply, we use the opposite of XPS, where instead of putting photons in and getting electrons out, we put electrons in and get photons out. The way the experiment works, this is some data, or this is a slide from the vendor here, Physical Electronics. We increase the energy of electrons that hit the sample surface, and we use a bandpass filter to let specific wavelengths of light through back to a photodetector. And so we measure these very, very low energy photons in a very lengthy experiment inside the instrument. And what that allows us to do is to look at conduction band electrons, where we're essentially filling up these unfilled sites until they give off light. And that allows us to kind of combine the information we get from XPS and UPS, where we look at the valence states, with what we get from LIPS, which are the conduction states. And then the distance between these two onsets is going to be the band gap of materials. So this is a relatively new technique. We're still learning this here at MCL, but anybody who's interested in this is encouraged to contact us. The researchers that tend to be interested in this kind of information typically are looking at organic photovoltaics or organic electronics, seem to be the folks that are most interested in conduction state phenomena and materials. So collectively, the kind of information and the measurements that we use to sort of map out these band structure information is shown here. In green, we can get the work function, the ionization potential, and the valence band maximum using some combination of XPS and or UPS. LIPS we can use to measure the conduction band minimum, vacuum level, and the electron affinity using LIPS. And if we combine all of these things, we can get, if we want to measure the band gap, depending on the material, we can measure that with either reals, UV-Vis, or the combination of UPS and LIPS, where UPS would give us the conduction band minimum. LIPS would give us the conduction band minimum, and UPS would give us the valence band maximum, and the sum of those would then, of course, obviously be the band gap. So up till now, I've talked about electronic measurements on single materials, but most electronic devices involve heterojunctions. And and studying those interface states can be a very important step in developing a material. So if we take two different materials that we then want to form a junction between, and I've just kind of mapped out here the cartoon of their band structures. The first thing that happens when we form a junction between these, that the Fermi levels align. And then there can be these conduction and valence band offset states that are important to be able to measure. What's shown here is a classic paper that went through how this was done with XPS. So let me quickly go over how we can measure these parameters using XPS on very specially designed samples. So it's critical for the measurement that we have essentially a thick version of each of the two materials that are going to be on either side of that interface. So for our purposes, thick means that they got to be greater than at least 10 nanometers. That's the maximum limit of the sampling depth of XPS. So beyond 10 nanometers, we don't really care what's down below here. And we will make some measurements of both core and valence band measurements on that pure compound. Also, I should point out that it requires that these samples be semiconducting. We'll make those same measurements on the other material, this being the substrate. Again, similar thicknesses here. Again, we're going to measure these absolute positions here. And then we need a very specially designed material here where you have a junction where we have a continuous film of one material on the other material. And that continuous film needs to be partially transparent to the XPS. So we need to be able to look through it and get a reasonable amount of signal from material B. At the same time, we're getting signal from material A. And so for practical purposes, that generally involves a film that's somewhere between 1 and roughly 7 nanometers in thickness. And we make some measurements on these same properties there. And then it's a relatively simple mathematical formula where we can measure the valence band and conduction band offsets. I think we also need the band gap to get the conduction band offsets, but we can measure these positions. And this is a good way to predict the properties of a junction of a material.
Thanks, Jeff, for sharing the many ways through which we can study the electronic band structure of your material. My name is Maxwell Wetherington, and I'm going to talk to you about ways for us to measure the carrier concentration in your materials via Raman spectroscopy. Raman spectroscopy is an inelastic scattering technique, and in a crystalline material, that means that we're actually studying lattice waves that propagate through your material, also referred to as phonons. The symmetry of those phonons are shown here, so we can have longitudinal acoustic modes, longitudinal optical modes, where the motion of the atom is in the same direction as the motion of the wave vector. We can also see transverse acoustic modes and transverse optical modes, where the wave vector is perpendicular to the motion of the atoms. So the particular symmetry that we're interested in when we're studying carrier concentration are these longitudinal optical modes, which can actually couple to what's called a surface plasmon, where you have charge carrier wave propagating along the surface of your sample. And the change in the polarization of the charges actually couples to that longitudinal optical mode. That results in a dampening in the frequency of that mode, and in some cases a broadening in the profile. And so we can actually use that dampening and the broadening of the longitudinal optical mode and correlate that to the plasma frequency, the surface plasmon frequency, which has a direct correlation to the carrier concentration. An example of this is silicon carbide. This is 4H polytype silicon carbide. And again, we're looking at the longitudinal optical mode in this particular system. And this silicon carbide was doped across, there was a gradient of the dopant across this chip. And we see from the edge towards the highest dope region, from A, the lowest dope, to E, the highest dope, we see this change in position and dampening, where you see this asymmetric profile. What we're plotting here in this graph on the right is the degree of that dampening, and then correlating that to the measured carrier density of the silicon carbide wafer. And here you can see that with that, the parameter of the longitudinal optical phonon dampening, we see that there's a nice linear plot over a range from roughly 10 to the 15 to 10 to the 18 inverse centimeters cubed for the carrier concentration density. So this is an interesting method where you can actually characterize the carrier concentration without making a device, and it is non-contact. So you can do this through a window if you want to study this particular system, let's say in a vacuum or some other non-ambient condition. And in addition to that, if you have a micro-Raman system, you can now map out the carrier concentration with micron resolution. Another example of measuring carrier concentration and strain in this case are in some 2D material systems. In particular, this is graphene, where a group identified that they could deconvolute the effect of both strain and carrier concentration on the and their effect on the Raman response via monitoring 2 different phonon modes within that particular material system. And when they deconvolute the peak position change, they are then able to then correlate this change to the carrier concentration and the strain percentage within the graphene system. I will mention, though, that this particular method does require an empirical relationship to be developed, whereas we need to know the band structure of your particular material. So we need to know things like the Fermi velocity, as well as the permittivity of the system to accurately correspond the shifts to these carrier concentrations and percentage strain values. So that concludes my portion of the talk. Thank you very much. I hand it over to Jeff.
So for more information about any of the measurements that you heard about today, feel free to visit our website and reach out to folks at MCL. Thank you very much.